Hi again. We are now going to record the first chapter essentially. Computability is a study of linear power of computation of various machines. And we will be presenting one of the first short problems that intrigued several scientists. And this is called the Diophantine equations problem. Stated simply, it is the existence of solutions to equations of this form. So since we already clicked on it in the previous quick introduction, we can actually go to that Diophantine equations notebook and try to run it. So having loaded the Python widgets, the exercise is trying to see whether the users can find XYZ such that a certain Diophantine equation is solved. And the widget will be allowed to range over X being -3 to 3, Y being -3 to 3, Z being -3 to 3. And so far, oh, you got an is solved already. So these values do not solve it. And I was lucky to get is solved this quickly. Usually it takes many tries. So you can now see the utility of the Diophantine equation widget in the sense the user has to experience an unbounded search over an infinite range. And that is the reason why essentially the certificate for Diophantine equations is not bounded. And the reason is discussed in various papers. So this actually gives the users a taste of computability and the search and the certificate, and the idea of recursive enumerability can be introduced, saying that you can enumerate all possible Diophantine equation solutions by systematically searching in increasing ranges. But if the equation doesn't have a solution, you cannot find it. So you could introduce these material. And we are now going to see which notebook is presented to us when we go to the next chapter, which is the basics of modeling strings, languages, and symbols and alphabet. This topic tends to confuse people needlessly because they are often confused by epsilon, empty set containing epsilon. But the epsilon is simply an empty string, and that is available in Python or any programming language. So you could actually introduce epsilon concatenation AB in Python using empty string concatenation AB and things like that. So this is what we will attempt to do in a notebook that is going to be presented to you. And so let's go into that notebook. And this is Computability and Languages notebook, which will cover the concepts of symbols and languages. And again, let us run this notebook and see how far we can run. Some of the notebooks have mathematical descriptions that will help you understand what is being mentioned below. So here we are going to model the existence of various concepts. We are going to present various concepts such as empty language, unit language, which is a language containing an epsilon. The reason it is a unit language is that if you view concatenation as multiplication, then when you concatenate the unit language with a language, you get that language back. The empty language is also called the zero language in what I described, in that if you concatenate any language with the zero language, you get the zero language back. This actually helps build intuitions, and you can actually play with this notion. And the concatenation and exponentiation, they're all introduced in a short set of Python functions. So I'll be very brief about it because these can be easily read and understood and explained. And so we'll let us run these cells though. I think these have been run. These cells have been run. This cell has been run. So now we can actually go to the next module, which is you can actually try each individual function. And let us say that we want to generate a unit language and concatenate the unit language concatenation is going to be illustrated in very soon. So let us say I generate a language called L1, which is all the a to the n for n in 0 to 3. So this is a way to generate it in Python as a set comprehension. And then we can generate concatenation of unit to L1, where L1 is already defined, I think. So let us define L1. I think it's defined. L2 is defined now. Now the concatenation of L1 and L2 can be understood. And then the concatenation of the unit with L1 returns L1. You can test that. The exercise, which includes concatenation of unit with L1. Let us ask whether L concatenation of L unit with L1, some language L1 equal to L1. So that is what a unit language ought to do, and it is true. So you can see that the concatenation for with units works. Similarly, you have other ideas here. So suppose you want to generate all the 0 raised to m, 1 raised to n, such that m is in this range. So you could actually see that this set of string concatenations of zeros followed by ones can be generated. So now let us continue illustrating exponentiation. So exponentiation of a language is repeated concatenation up to the degree mentioned. And the definitions for exponentiation itself is interesting to read. So if you exponentiate a language L n-fold, what you get is the unit language if n is 0. So the 0th exponent is the set containing epsilon, or the unit language, which is very handy now. It's almost like x raised to 0 is 1 for a number. So that is the kind of convention that helps out. Otherwise, it is concatenation of L with the n-1th exponent, which is how exponentiation is defined. So that actual definition is highly teachable. And now you can find various exponents of various languages in this manner. And now if you look at the Kleene star, which is the next definition that often students stumble over. Star is has to be truncated to size n, because star is going to generate an infinite number of unions. So let us see what it reads like. So if you star a language up to degree 0, it is again the unit, because you're going to include or union the unit language. Otherwise, it is the union of the nth exponent with a star recursively applied for n-1 iterates. So the Astor rate, as Dexter Posen calls for L star, is obtained by doing this repeated concatenation of languages and union. Okay, so at this point we can now exercise the star using widgets again. So let us take a widget oriented piece of code. Here there are 3 languages introduced, and we are going to consider the star of these 3 languages. So let us take L1, and it is the epsilon followed by BC. Those are the strings in the language, and choose L1 here. So now the 0th star application is always an empty string, set containing the empty string, which is the unit language, because star has not been applied sufficiently. As soon as you apply star to some more size 1, it gives you the original language. Now, if you apply the star up to size 2, it is basically going to take the unit language, union, the L1 language, union, the concatenation of L1 with itself, which gives you the BC. So like that, you can expand the star and see the language, produce all the strings, and the students can easily understand that the limit of this construction is what star is. Now let us look at the M language and apply, and the star is indeed pretty large, so we can avoid looking at all of that. It already got very large, so I have to locate where the top is. So here you go. And let's do a shorter degree of starring of M, which is shorter. And you can also choose the empty set or empty language and star it. And any number of stars of the empty language is set containing epsilon. It's not empty set, because the star of any language includes the epsilon. So now if I take the unit and star it again, you get that. And you can mention that these are the two cases where the star produces a finite tree set. In all other cases, you get an infinite set. And the L star up to n has to be extended to infinity to see the full extent of the star. So this notion ought to be clear in that you can understand various language constructs piecemeal. And that is what this notebook is about. There are other functions such as homomorphisms, reversals, this symmetric difference, things like that, power sets. All these are in this module, so you can actually run and also read the code. I highly encourage you to do that. And with that, I think this notebook will end with all these illustrations. So this actually covers the basics of symbols, strings, languages, string operations, which came up implicitly, string concatenation, string exponentiation, language concatenation, language complement, union, intersection, and the star. So let us see how the complementation is done, because the complementation is an interesting concept that you need to introduce. So we know that complementation needs the use of a universal set, because you're essentially removing from the universe the items in the complement. So here's one use of complementation. So what I do is I'll run this cell. Let us say I have the language L4, and I have some printouts also. So complement of the L4 language with the alphabet involved being 0, 1. And I'm taking the star degree to be at 1 is this one, because it takes everything in the star up to degree 1 and removes. So removes from that language. So basically, let's run one of these. So separately, because the printouts are a bit cluttered. So I can print out, or L sound complim is the function. And the language in question is L4. And I had to give a certain alphabet over which the universe is being formed. And let us say I'm going to give it the size 4, and let's see what it says. So it actually gives you a universe of 0, 1, L star 4. So let us look at that. L star of the L star requires language and a bound. Okay, so we can use the star can be applied to any language, but it can also be applied to an alphabet. So when we apply to an alphabet like that, it produces the star of that alphabet up to size 4. So now if I take the complement, let's reduce all these numbers to 2 and make it easier to visualize. So star up to 2 has this one, and now complementation of some language. So let's make a certain language, my lang equal to, let's say my language contains epsilon and 0. That's all. Or maybe 1, 1. So that's my language. So now I want to complement my language. And the alphabet for the complementation is 0, 1. And I had to apply the same degree of star. Then what do I get? So I get 0, 0, 0, 1, 1, and 1, 0. So it eliminates from the star the epsilon. It eliminates 0. It eliminates 1, 1. So that's what complementation should mean. It subtracts from the universe the language being complemented. So that is indeed happening. Similarly, you can build symmetric differences and things like that. So I think this ties together many things that you may want to introduce in your course. And here is a Python-based medium for exploring these. And there are very, very interesting constructs that come in automated theory. So suppose you want to take this BCs which is a certain set. I had to run this BC set and then see the BCs, which is all these B's and C's according to I in range 8. So B raised to I followed by C raised to I for I in range 8, which is included here. And now suppose I want to make this C raised to J for I in range 8, for J in range 8. And suppose I want to introduce I less than J, then this can be a different language, which now includes less B's than C's. And these are the kind of restrictions that often are used in introducing languages. And Python is an excellent medium for introducing these kinds of definitions, contrasting it with the mathematics that you might have written to express the same things. All right, so this is the language module. So next, we actually start introducing DFA, NFA, and machines, and that's where we'll go next time. So see you at that module. Thank you, bye.